In the previous video, I gave you some introduction on this mobile robot model made using Simscape and Simulink. And now we're going to dive a bit deeper into the details. So you can see here the robot, and I have highlighted the three axes. So you can see blue is Z, green is Y, and red is X, okay? So now we're going to refer to these three axes when we look at the Simscape. What we can see here already is that the frame, so the body, which is the yellow, which is this three axis here, the ground, which is these three axis here, and the sphere at the front, they have the same orientation. Whilst the two wheels are rotated by minus 90 degrees on the x-axis. And this is because the revolution joint on the wheels is on Z, okay, because that's how Simscape works. Okay, let's look at Simscape. So this is the model, which should be a bit familiar. We said that we have the solver configuration here, and I think I gave an introduction on these three things here. So the most important thing is the wall frame. Then from the wall frame, we have a rigid transformation to position the object. And downstream of this transformation, we have the 6 degrees of freedom joint, which basically means that the object is free to move in any way, right? Which is what it is. There's no joint connecting the robot to the world other than the contact force with the ground, essentially, right, with the floor. But this transform is here mainly to make the robot start from a sensible position, okay? So we don't want the robot to start from flying or sort of merged into the ground. And this is what it does, okay? So let's have a look. So we have no rotation, and then we have a translation on plus Z. This transformation is a translation on Z, and it basically lifts the robot a little bit, right? Because if we have no transformation, we would start with the center of mass of the robot at the same level as the center of mass of the floor. So the robot would be inside the floor. We want the robot to be a bit higher, and how much we want it to be higher is either half the body height or how much the wheel is translated on the z-axis plus the radius of the wheel, okay? And ideally, we want the second one, because otherwise that means we have configured the wheels in the wrong way, because the wheels, we don't want them to be inside the robot, okay? But this is just a kind of a safeguard. If we make the wheel very small and not translated, we will start with the robot on the floor, with the body of the robot touching the floor, which doesn't make a lot of sense, but that's what we would get. Okay, so this is the first step. Then from here, we have the joint. We extract the speed on the x-axis, y-axis, and the quaternion that is identifying the rotation of the robot, and we translate it into the heading, into the yaw angle. And then we take the two speeds, and we calculate the speed, basically the vector, right? So this is the absolute speed over the plane that is forming the ground. Okay, then from that frame, we have, if you follow this line, we go to the body. The body is a cylinder, and we can see the cylinder here. I gave radius is the parameter, length is the other parameter that we configured. Then we say that we want to export the geometry for the contact forces. Then the inertia is basically calculated from geometry. So this means we are telling it the density, which is the density of plastic, as I said in the previous video. And it will calculate the inertia and everything from that. And then in graphic, we can decide the color and transparencies, a bit of simple stuff there. Okay, so this is the body. Then from the body, we said to export the geometry. This is the geometry link. So we link this geometry to the spatial contact force. And that is also connected to the infinite plane, which is the ground essentially, okay? And this will reproduce contact forces that are identified by a few things that I mentioned last time. So Simscape basically models the contact as spring and damping. So we have the stiffness, we have the damping identified, and then we have the friction that is identified again as coefficient of static friction and dynamic friction. And then we have the critical velocity, which is when Simscape decides that the friction is either static or dynamic. Okay, then we have other transforms to go to the three wheels, basically, if we include the sphere as a wheel. So to go to the sphere, we move on X and we move forward, okay? Remember that X looks ahead, okay? X looks on this direction, is the red one. So we go positive on X by a parameter that we have configured. Let me go back to Simulink. We go positive on X and we go negative on Z because we want to go a bit down, right? And these are two parameters that I gave some numbers to in the init file. Similar for the right wheel, we go negative on X because we want to go back. Then we go positive on Y because we go right. And then still negative on Z, same amount as the front sphere. And now we see that the left wheel is exactly the same as the right wheel, except on Y where we go negative because we want to go left. And obviously, I forgot on the previous wheel, we have this rotation of minus 90 degrees on X. So let's look at the model. We said this before. So you can see that these axes are rotated by minus 90 degrees around the x-axis, which is the red one. Then we have same things for the, okay, maybe let's go through the joints first. Okay, so after the transfer, we are moving the wheel, we are rotating the wheels, and then we have a joint. Okay, so for the front sphere, we have a spherical joint. So the sphere can rotate around any axis, basically. It's just fixed in the center. So this spherical joint has a few things, has a damping coefficient, which we, no stiffness, damping coefficient, which we have selected before. I said that I have selected these coefficients to make sense, essentially. There's no actuation on this joint because it's a non-actuated joint for the sphere. It just rotates to make the robot move more smoothly without touching the surface, touching the floor. For the other two wheels, we have a revolute joint. So we can rotate only around the z-axis. So remember, the z-axis of the wheels is across this direction. It's the blue one here and the blue one here. So z-axis We have same damping coefficient, no stiffness. We also have actuation here, okay? So torque is provided by input because we are controlling the wheels in torque for now. And we have the same thing for the right wheel here. So identical stuff, okay? Identical stuff. Then from the frame of the three joints, we go to the right wheel here, to the left wheel here, and to the sphere. Right wheel is an elliptic solid, so we give it the 3 radius, okay? So radius on X, on Y, and on Z. Always the same, except for Z, which is half. Just a choice. Sorry, I made a mistake. On Z, it's width will divided by 2 because it's a radius. Okay, so this is how I made the shape. We want to export the geometry for the contact forces. Inertia is calculated from the geometry as before. We give it the density, and then we have the graphics where we set the color and yeah, the appearance basically. Right wheel, left wheel is identical, same stuff. So we have, okay, no graphics. We have the density, we give it the density, we calculate the inertia from the geometry. The sphere is also similar, just slightly different color, and we have only just one radius because it's a sphere. We also export the geometry, inertia we calculated from the geometry, we have the density, same stuff. And then we have the contact forces exactly as before. So as the body, obviously, this contact force, we don't really expect it to do anything because the bodies should never really touch the ground. But these 3 will basically be the ones that make our robot work and move. So we can have a look, but they are exactly the same as the other one I showed you. Then we have the 2 torques that, as I said, it's a repeating sequence just to make the robot do something really. I filtered it with a low pass filter, first order. Then it's converted to a Simscape signal from Simulink. So here we are in the Simulink world. Here we enter in the Simscape world, and we go in the revolute joint, so to actuate the joint. Okay, this is it. Just have a look at how the robot works. Just let's take a look at the video. Okay, maybe we can, yeah, we can remove the axis and play the video. And this is what it does with the torques that we decided. Okay, we have already seen this video. Okay, this is it for today. Thank you for watching.